Hello Year 10. Today we're going to be learning about accuracy of measurement and instruments. But before we do that, let's revise some work from last lesson. We were talking about area. So question 1, we want to find the area of that shape. That shape is a rhombus because it's a square that has been pushed over, so it's no longer right angled. The formula for that shape is A equals half x y, where x and y are the diagonals, which are these numbers that we've been given here. So the 10 and the 15. So it's half times 10 times 15. That makes 75 centimetres squared. Question 2, to find the exact area of the shape shown, the shaded section that is referring to. What we would do is we would find the area of the outside rectangle using A equals BH, and then we would subtract off half of a circle, so half of pi r squared. Subbing into the formula, the base and the height of the rectangle is 10 times 20. Then the circle, we have half times pi times the radius of the circle. The 10 would be the diameter, so the radius here would be 5, so 5 squared. Giving that answer to 2 decimal places, you get 160.73 centimetres squared. Okay, so we want to talk about accuracy of measurement. So if this diagram down here was a very big enlarged picture of a measurement shown on a ruler, so you might have had on a meter ruler, you might have had 45 centimetres, 46 centimetres and 47 centimetres. So when you look at that really, really big as it is, if you happen to have a measurement that was exactly on the 46, we know it's on 46. But in real life, things aren't always perfect measurements, and you might find you actually had something that might have been looking like it was about here. Now, if you were measuring in centimetres to the nearest centimetre, you go, well, it's still closer to 46. And any line that you do all the way up to here, you'd go, well, that's halfway between. I could still potentially round that to 46. So we always have an error of half of our smaller unit of measurement. So if we measure in centimetres, it could be half a centimetre smaller, going down to 45.5, or it could be half a centimetre bigger, meaning that it could be all the way up to 46.5. Okay, so if we want to find the limits of accuracy, this is our formula. We have plus or minus half times the smallest unit of measurement. And I've just given the example of, if it was centimetres, it would be half a centimetre up or half a centimetre down. What if we had something to 1 decimal place? So we have 45.8, 45.9, 46, 46.1, 46.2. So if I've measured things to the nearest 1 decimal place, then all the way up to 46.05, could anything up to there, so a line in here, it would round to be 46. Or anything half a space down would round up to 46. Okay, so half times the 0.1 that the scale of that ruler is, means it's 0.05 up and down from the 46. So 46 plus 0.5 is 46.05. That could be the highest the measurement could be. Or if you take off the 0.05, it'd be 45.95. Anything between that could be the real measurement. Okay, so what are we going to do with this? Let's go to our examples. Example number 1. Consider the diagram. Use Pythagoras' theorem to find the length of the diameter of the semicircle rounding to 1 decimal place. Okay, so we have a right angle triangle here. there and there. And I want to find the diameter of the circle, which is going to be the hypotenuse. So we go h for hypotenuse equals square root of a squared plus b squared. And subbing in my numbers, I get 10.6 squared plus 8.7 squared. To one decimal place, that gives me 13.7 meters. Okay, now that's a rounded answer. I've rounded that to one decimal place. Let's have a look what happens next. B says, using your answer from part A, find the area of the semicircle and round to one decimal place. Okay, so the area of the semicircle should be half of pi r squared. Okay, now 13.7, let's type this in. We had 13.7 was our diameter. If we divide that by 2, we have 6.85 as the radius. So it's half times pi times 6.85 squared. Let's type that in. Half times pi times 6.85 squared gives 73.7 meters squared for the area. Part C, find the area of the triangle, rounding your answer to one decimal place. The area of the triangle is half base times height. The base and the height are the 10.6 and the 8.7. That makes 46.1 meters squared. Hence, find the total area. The total area of that shape is going to be adding those last two results together. So 73.7 plus 46.1, which is 119.8. Okay, that all looks good and normal, but what does part E say? Now recalculate the total area by retaining more precise answers for part A through to C, and then only at the very end, round your answer to one decimal place. So if we go all the way back to finding our hypotenuse back here. So if I type this in again, we have the square root of 10.6 squared plus 8.7 squared. So let's keep 4 decimal places. So we'll go 13.7131. Okay, then from that, we found the area of the semicircle, which was half of pi r squared, which is half times pi times that h was a diameter, so dividing that by 2, we get 6.8566, which is 10.77. Wait, sorry, I forgot the squared. That will make a difference. There we go. 73.8477. The area of the triangle was half base times height. The calculation was up here. If I type that in again, we have half times 10.6 times 8.7. It was actually 46.11. So there was an extra decimal place there that I could keep, which means the total area of that is 73.8477 plus 46.11, which makes 73.8477 plus 46.11, which is 119. We wanted one decimal place, so it would be 120.0. And that would be meters squared. Now, it's not much of a difference, but by keeping more decimal places, you can see that there is a small difference between the two results that I have given there. Anytime that you do a calculation where you are rounding answers, you are creating an error in the results that you have got there. Okay, and the more calculations you do, the larger that error is likely to become. Okay, part F. Compare your answers to part D and E. How can you explain the difference? So let's subtract them. We would say our 120.0 minus the 119.8 is a 0.2. So there is a 0.2 difference in the answers, and this is due to rounding errors. Okay, what else can we do? So now that we know that our measurements can create errors, we want to be able to see just how far out our measurements could be. In question 2, we want to state what the limits of accuracy are for the measurements that have been given. So this is using that formula that the limit of accuracy is equal to plus or minus half the smaller unit of measurement. So for 24 centimetres, it is going that what has been measured here is to the nearest 1 centimetre. So using the formula would be plus or minus 0.5 times 1. 0.5 times 1 is plus or minus 0.5. Okay, to work what that out as a measurement, if I subtract 0.5 off 24, the smallest my measurement would be is 23.5 centimetres. If I add the 0.5 onto 24, I get 24.5 centimetres, which means the real measurement is somewhere between 23.5 and 24.5 centimetres. Part B, the question has been rounded to 1 decimal place, which means this has been rounded to the nearest 0.1. To calculate the error, we do plus or minus 0.5 times the 0.1, which makes plus or minus, and you can times them together in your calculator if you need to, 0.5 times the 0.1, and you put the plus or minus onto that, 0.05. So to work out the lower measurement, you start with 38.4 and you subtract the 0.05, which means the smaller measurement is 38.35. And that's in millimetres. Then 2, to get the bigger measurement, you start with your 38.4, which was your original amount, and you're going to add the 0.05, which is 38.45 millimetres. Question C. This number, 8.237, has been rounded to the third decimal place, which is 0.001. So our limit of accuracy is plus or minus 0.5 times the 0.001, which makes plus or minus 0.0005. And again, finding those numbers, you type in 8.237 and then you minus 0.005. Oops, I missed a 0. To get 8.2365. And that's litres. To find the second measurement, we just want to add that result on instead, which gives 8.2375 litres. Question D. This number here has been rounded to 2 decimal places, which is 0.01. Our limit of accuracy is going to be plus or minus 0.5 times that 0.01, which is 0.005 millilitres. Subtracting that measurement from 2.86, we get 2.855 millilitres. Then we want to add the measurement on and get 2.865. Okay, question 2. Trevor measures the sides of a square to be 8 centimetres. Find the upper and lower limits for the sides of the square. Okay, so that has been measured to the nearest 1 centimetre. The limit is going to be plus or minus 0.5 times the 1, which is plus or minus 0.5. Now, if we do 8 minus the 0.5, we get 7.5 centimetres. 2, if we start with 8 and add on the 0.5, we get 8.5 centimetres. The 7.5 is what we call the lower limit, and the 8.5 is the upper limit. So if I then proceed to part B, the upper and lower, we want to find the upper and lower limits for the perimeter of a square. So if you want the lower limit for the perimeter, you would use the lowest measurement, which is 7.5. The perimeter of a square would be 7.5 times by 4, which is 30 centimetres. The upper limit would be using the larger measurement, which is 8.5. And you times that by 4 to find the perimeter, which makes 34 centimetres. So simply by rounding the side of that square to 8 centimetres, the nearest whole centimetre, the error in that measurement means that the real perimeter could be anywhere between 30 and 34 centimetres. Now let's look at area. We want to find the upper and lower limit of the area. So again, if we want the lower limit, we want to find the area, which is L squared, using the lower measurement, which is 7.5. 7.5 squared is 56.25 centimetres squared. The upper limit, using the area formula again, it would be 8.5 squared, making an area of 72.25 centimetres squared. And that's a much bigger difference. The lower limit of 56 to the upper limit of 72 is a much bigger gap because we were squaring those numbers. So that's what errors can do to your calculations. You need to practice finding some errors now in exercise 4H.